processes a vast amount of data. To process this data, it requires a memory so that it can remember all the data. A magnetic tape is one of the storage devices used by a computer system. Another device used is the Winchester or the hard disk. The computer uses integrated circuits or ICs for various operations, including storage of data. A circuit made up of a large number of components fabricated on a single chip is called an IC. The question is, what is the basic electronic circuit which has a memory? The flip-flop is the basic storage circuit. It has control inputs and two complementary outputs, Q and not Q. One is the complement of the other. A flip-flop stores one bit at a time, either a 0 or a 1.
It remembers its output even when the input is changed.
How is a flip-flop circuit realized practically? This particular circuit uses transistors and resistors . This is a bistable multivibrator circuit, also known as a latch circuit. In this circuit, when T1 conducts, T2 is forced to cut off and Q is equal to plus 5 volts and is latched at logic level 1. Similarly, when T2 conducts and is in saturation, T1 is forced to cut off, Q is then at 0.2 volts and is latched at logic level 0. So either T1 or T2 can conduct at a time. In this latch circuit, we now introduce two control inputs, the R or reset input and the S or set input. A bulb glowing on any line indicates that that line is at logic level 1. A positive trigger at S input only makes Q equal to 1. This is set state. R equal to 0, S equal to 1 makes Q equal to 1. R and S both at ground cause Q not to change. This is no change condition. A positive trigger at R input only causes Q equal to 0. When both R and S inputs are positively triggered simultaneously, both T1 and T2 try to turn on. Any transistor takes a finite time in turning on. As no two transistors are identical, T1 and T2 have different turn-on times. So they race and the faster one wins and starts conducting. Q is latched at logic level 0 or at 1 depending on whether T2 or T1 is faster in turning on. The truth table summarizes the operation of the RS flip-flop. R equal to 0, S equal to 1 makes Q equal to 1. R equal to 0, S equal to 0 is a no change condition. R equal to 1, S equal to 0 makes Q equal to 0. R at 1 and S at 1 is a forbidden condition. This is the race condition. The same flip-flop is now realized using NAND gates. The NAND gate, when R is 0, S is at 1, Q is 1 and not Q is 0. R at 1 and S at 1 does not make Q change. This is no change. When there is a positive trigger at R alone, Q bar is 1 and Q is 0. R and S at 0 cause both gates to race between themselves. This is a race or forbidden condition. The truth table summarizes the operation of the NAND flip-flop. Note that R0 and S0 is a race condition and R1 and S1 is the no change condition. Remember this, for we shall refer to it again later. The RS flip-flop is now built using NOR gates. A positive trigger at S input only makes Q equal to 1 and not Q equal to 0. Both R and S at 0 causes Q to remain unchanged. A positive trigger at R input alone causes Q to be 0 and not Q to be equal to 1. When both R and S are given positive triggers simultaneously, it results in a race condition. This condition is not allowed. At R equal to 0, S equal to 1, Q is equal to 1, not Q equal to 0. At R1 and S0, Q is equal to 0, not Q is equal to 1. Note the difference with the NAND RS flip-flop. R equal to 0 and S equal to 0 is race condition for the NAND RS flip-flop. For the NOR, it is the no change condition. R equal to 1 and S equal to 1 is the no change condition for the NAND flip-flop, while here it is the race condition. Another very important aspect of the flip-flop is the clock signal. To understand this, let us have a look at a traffic intersection. The policeman regulates and synchronizes the flow of traffic. A computer system uses a number of flip-flops. Taking a look at this circuit of many flip-flops, as the input data arrives in the form of pulses, the output varies randomly. If a computer system worked like this, it would be completely disordered. So to regulate this, the clock signal is used. This synchronizes the working of the flip-flop just as the policeman was regulating the flow of traffic. Now, as the input data arrives, the clock signal causes the outputs to change uniformly and only at certain specified instants of time. This is much more ordered and the whole system can work synchronously. A square wave is generally used as the clock wave or the triggering input. This is a clocked NAND RS flip-flop. It has an additional input, the clock input. The signals of this flip-flop with respect to time are shown in the timing diagram. Now, when clock is at 1, R is at 0, S is at 1, Q goes from 0 to 1. With clock at 1 again, R at 1, S at 0, Q changes from state 1 to 0. Note that the flip-flop changes state only when the clock level is at 1. This is called positive clocking. The positively clocked RS flip-flop responds to its R and S inputs only when the clock level is at logic level 1. The NOT gate on the clock line indicates that this is a negatively clocked RS flip-flop. Note from its truth table that it responds to the reset and set inputs only when the clock is at logic level 0. Let's review the main features of the flip-flop, especially the RS flip-flop. A flip-flop is the basic circuit storage element. It can store one bit at a time, either a logical 1 or a logical 0. The RS flip-flop has two control inputs, the reset and set and the trigger input clock, and two complementary outputs, Q and not Q. A flip-flop is said to be in the set state when Q is equal to 1 and not Q is equal to 0. On the other hand, it is said to be in the reset state when Q is equal to 0 and not Q is equal to 1. The clock input synchronizes the action of flip-flops. A positively clocked RS flip-flop responds only when its triggering level is 1. Negatively clocked RS flip-flop responds to the clock level being 0. The positively clocked RS flip-flop changes only when its clock level is at 1. The truth table for a negatively clocked RS flip-flop shows that it responds to its R and S inputs only when clock input is at logic level 0.